So far we have learned ways to calculate the kinetic constant. We have been able to identify that depending on the order of the reaction, so if you plot the logarithm of a concentration versus time, for a first order reaction the slope is a given constant, kinetic constant, which is constant throughout the reaction, K, our kinetic constant. If it's second order, we have to plot the inverse of concentration versus time, and then the slope will also give us the kinetic constant. All these experiments are done, and that's important to remember, at temperature constant. Okay. Now, if we change the temperature, we are going to change the kinetic constant. To what extent? Well, say that we set up different experiments, and in each experiment we calculate a kinetic constant at a different temperatures. Notice that in here we increase the temperature and we calculate the kinetic constant. So for each of these experiments, one would need to plot one of these plots, get the slope, and therefore calculate the kinetic constant. What we see is that every time we increase more or less the temperature by 10 degrees, the kinetic constant pretty much doubles. Okay, notice that the concentrations in here of reactants are all the same based on the units of the kinetic constant. This is a second order reaction, but there is a very strong dependence of the temperature. So what kind of dependence is that? Well, as you can see, if just by increasing 10 degrees of temperature the kinetic constant doubles, that's yet another exponential dependence. All right. So now our scope on this video is how can we figure out what is that explicit dependence? In what way the kinetic constant depends on the temperature, and as we see, it should be somewhat exponential. It should be something that it should really increase with the temperature in an exponential manner, whatever that is. So let's try to find out or try to rationalize in what way or what factors affect the kinetic constant. Well, first, maybe the most intuitive answer is, could it be that there is an increase of temperature that increases exponentially the number of collisions? Because of, as you well know, the temperature can affect the collision frequency. So a reaction to take place, the reactants need to collide with each other. Not only collide, but they also need to collide with the right orientation. And finally, they also need to have enough energy. So this collision has to have enough energy so that reactants can reach products. Now, the first question is, could it be collision frequency? Let's look a little bit into that and see if the collision frequency depends exponentially, as we saw, with the temperature. Well, what we can figure out from kinetic molecular theory is that the speed of a molecule, therefore the number of collisions, depends with the square root of the temperature, not exponentially. So for example, if one tries to calculate what ratio of collisions do we have at 318 Kelvin versus how much we had at 298, if it depends on the square root of temperature, the increase is only by this factor, by 1.033. So the collision frequency has only increased by 3.3%. However, we saw in here that by increasing 10 degrees, we have pretty much almost doubled the kinetic constant. By any means, this is the factor that we have seen experimentally. Therefore, the number of collisions cannot explain the dependence on temperature. So something that, Van Toff figured out, and then Svante Arrhenius was able to explain, is an experimental observation that shows us the dependence on the temperature of the kinetic constant. I will explain one by one what each of these terms mean. K is the well-known kinetic constant. The E sub A is the so-called activation energy, and activation energy is, if it's not the number of collisions, it has to be related therefore to the necessary energy that it takes to reach products. So when you have a reaction, you must think of the necessary energy. So these are your reactants, these are your products, the necessary energy to go from reactants to products. This will be your activation energy. R is the well-known gas constant. Just pay attention to the to the units. It's joules over mole and Kelvin. Therefore, the units of activation energy has to be in joules. So depending on the units you use on R, these have to be compatible, because remember that the exponent cannot have any units. T is of course the Kelvin temperature, and this is what our collision factor is. This is what it explains a little bit how the number of collisions affect the kinetic constant. Well, we have seen that it somewhat depends on temperature, so careful. It is considered constant among small range of temperatures, but we have known that it somewhat depends a little bit on the temperature. It depends actually on the square root of temperature, but it changes very small, so we're going to consider it within small ranges of temperature constant. And the most important factor, therefore, is this one. So how can we interpret the Arrhenius equation? Let me just go one by one. If we say that A can be considered the number of collisions, this factor here is considered as the number of collisions with sufficient energy. Sufficient energy to reach products. Okay, and this one does really depend on temperature. Okay, so notice that it's in the denominator, but this is a negative in here. So as you increase the temperature, you will see an exponential dependence with the kinetic constant. Okay, a little bit more of explanation. If you think of a first order reaction, the units of the kinetic constant is second to the minus 1. What does that mean, 1 over second? What seconds? Well, you can think of the kinetic constant as how many effective collisions reach products. So this gives you the number of collisions. Therefore, if your barrier up here is 0, so if you have a 0 barrier, so notice that here there would be no activation energy, the exponent on the Arrhenius equation is 0, therefore this is 1. This means all collisions, because A tells us the number of collisions, reach two products. Therefore, the exponential component will tell us what fraction of those number of collisions will have sufficient energy. This will always be a number below 1, so A, this number of collisions, is the upper bound limit of how many collisions could potentially reach products, and the exponential factor tells us, well, out of those number of collisions, only a small fraction will reach products because of the energy barrier and because of the temperature that those molecules have. Okay, let's solve a little bit of a simple problem. In this case, this is mostly plugging in numbers, but it also will help us understand a little bit more what kind of questions we are able to answer. It's asking for what fraction of collisions will have sufficient energy to react for a gas whose activation energy is this much. Well, we just said that the Arrhenius equation contains two factors or two components. This is the number of collisions, and this is what is the fraction of those collisions with enough energy. So this is what we are actually being with enough energy to reach products. So we are being asked about this number. So the answer to that is we want to plug this in. It says 68 kilojoules per mole. So that means 68,000 joules per mole divided by R, which is 831 joules over mole and Kelvin, times the temperature. And the temperature in here is 25. So 25 Celsius times 273, because you have to have it in Kelvin. Notice that Kelvin and Kelvin disappear, mole and mole disappear, and joules disappear. So this is correct. If you plug this into a calculator, and I forgot the negative sign here, you will see that the number is this much. So this gives you an extent of how small the fraction of collisions can actually reach products. This is fairly small. This means In 1,000 billion molecules, only one would have enough energy. But think of that when you have a mole of molecules, you have molecules of the order of 10 to the 23, so you still have a significant amount of molecules able to reach products. We'll keep practicing more, but it's very important that we have a conceptual understanding of the Arrhenius equation. I will insist it again. Number of collisions, this is our prefactor, and this is considered constant, even though we know that it's not exactly constant. It depends on the root square of temperature, but it's considered constant. And this factor that depends on the temperature and the barrier.